In the last video, we saw that we could create what's called a standing wave by having a wave that's traveling to the right, as you can see here on the screen, the top one, and then one that's traveling to the left. And when they crash into each other, when they add, we get what you see down at the bottom, which is a standing wave. And you can see that we've got points where we've got peaks, and then we've got points where we've got nodes, these points that never oscillate up and down. So if I go through this fairly slowly, we can see, just like we saw before, there's this place where we have completely constructive interference, and then completely destructive interference, and then when they add up, we can get constructive interference. And so we can have different points along here where we can characterize what's going on. So here's the same standing wave, similar to the one you just saw in the simulation, where I've got a snapshot view of what's going on. And notice that if I'm sitting on a raft right here, my raft is undisturbed, because a little time later, this is going to get, say, a little smaller like this. It may eventually get flat, and then it will go this way and go up, and this way and go like this. And when we see this as sort of a demo, this can go up, what happens, ooh, that's not very good. What happens is we see the nodes, that's what this is. This is our node. And we have a node here and a node here. And these taller areas are what are called antinodes. Okay, where it oscillates. The antinodes oscillate from the maximum here when the two waves add together to the minimum when they are both negative, and then sometimes in the middle when we have constructive interference. And so we can describe this wave in much the same way that we did before, except we only get standing waves when we have a situation where we can fit the right number of wavelengths of the two waves that are adding together, or the wavelength of this, in between the nodes that we're looking at. So our constraint is we have these 2 points, and we can set, for example, this side oscillating, so this can be oscillating up and down, and it sets a wave on this string, for example, between here, but it needs to be the right frequency, so we can set up an even wave so that when we, for example, have a wave that comes like this, it hits this end, turns around, and comes back the other way in just the right way so they add up. So we want this frequency to be such that the frequency times the wavelength is equal to the speed, and remember that speed is set by the tension in the wire and the mass per length. And the length that we want, in this case, notice, if I just look at this, that what we've done is we fit one wavelength into the length of string that we have here. If this is our length of string, then that is a situation where we can have one wavelength. We can set up a situation where in this same length, we can set up what is effectively half of a wavelength. It can turn around and kind of come back like this. Notice this is half of a wavelength, because that would be a full wavelength. So we can have, so lambda equals L, I'll put that beside where it is. So our wavelength equals L here. For this setup, this is called the fundamental frequency, and everything else is a higher harmonic. For this fundamental frequency, notice that our length is equal to half a wavelength. And the next one we can do, if we just set this up, is that we can kind of go 1, 2, all right, can't quite fit it in. Let me make the like this, okay, and notice that here is our wavelength, So now our length is 1 wavelength plus a half, or 3/2 of a wavelength. So what happens is we have a situation where the velocity, the speed of the wave speed gets fixed, is fixed by the tension and the mass, and then the length gets fixed by how far apart we put these posts. And so what we would do is we change our frequency, which will in turn change our wavelength. Change the wavelength. And we can measure these the same way we did before, right? We can measure from this point to this point, the same thing. That gives you the wavelength. It's actually the wavelength of each of the waves, one going one way and one going the other. And we can use our raft point of view to time how long it takes to go from here up and back down to get our period if you want, and then 1 over that is the frequency. So everything stays the same. It just allows, these are conditions for standing wave. So what we're setting up is the conditions for a standing wave. And when you pluck a string, like when you have a stringed instrument and you pluck it, what happens is the wave that sort of survives is this fundamental. This fundamental wave is the one that survives. So that's the note. And then you get some harmonics that also survive, oscillating back and forth. So you get what are called higher harmonics, and that gives you the characteristic sound of that particular stringed instrument. But our conditions for our standing wave are that, we can sort of see it coming here, that our length is either half of a wavelength, our length is equal to the wavelength, or 3/2 of the wavelength, or we can write it like this, that the wavelength is 2 over n times L, where n is an integer, which means it's a number, or we could say L is equal to n times lambda over 2, right? Because this is, for this one, this is n equals 1 right up here. This would be n equals 2 in this expression, right? L is equal to 2 lambda over 2, and this is L is equal to 3 lambda over 2. So either of these ways are ways to look at our condition for getting a standing wave on a string. And so these are the fundamentals. And this translates to standing waves in tubes, depending on whether the end of the tube is closed or the end of the tube is open. So for those of you who might have some experience with wind instruments, you're setting up the same kinds of conditions, except that when you have an open end of a tube, what happens is, instead of a node at the end, like we have here with the string, you end up with an antinode. But that's going a little further than we have the opportunity to go in this class. But if you've played an instrument, then you've probably either plucked a string or set up some kind of an oscillation, because what you want to do is set up an oscillation of sound waves to travel to the ear, and what we hear are notes are these regular ups and downs, and that's what happens when we have a vibration of our eardrum, and then we translate that into our note.